All right, so I'm going to share a screen, a blank screen, so that way I can ink the information for you. So the start of this unit basically began with you guys learning how to draw the electron dot diagrams for certain atoms. So there's things that we're going to have this right here. Let's see. I'm going to pen ink it, make it black. There we go. So there's things that you learned. You learned that the dot was an electron. And I'm going to refer to what vocab words you kind of need to focus on. Covalent bonds. So we need to define what covalence means. Covalence means that you're sharing electrons. And you're going to really get sick of me saying the word sharing, because I'm going to be referring it to sharing and sharing and sharing until we remember that that's what the unit is focusing on. There are types of electrons or atoms that don't share. They actually give and take. And from Unit 2, we learned that they are ionizing. So if they give an electron away, they become +1, +2. And if they're taking in electrons, they become more negative because they're taking it in. So there is something called ionic compounds that give and take, but our main focus for this entire unit is covalent, which is sharing electrons in a bond. Okay, so sharing electrons. We need to figure out who shares the electrons. So simplistically, if we're looking at the periodic table, we found that trends on the periodic table, that on the left side, these are your metals. On the right side, we have nonmetals. What you're going to find through all these examples that we're going to be doing is, if you notice where they're located or which atoms I'm having you do is, or use rather, non-metals with another non-metal, not no metal, non-metal, is giving you covalency, covalent bonds, or otherwise known as a covalent molecule. Okay, so that's what it's called, covalent molecule. So there's sharing occurring. Okay, we're going to talk about what kind of sharing can occur. There can occur equal sharing or unequal sharing, and we'll get to that today as well. So first I want to start off with the exact example from your worksheet number 3, which is your homework assignment. So I'm going to do the first one with you as an example to go step by step of my expectations for this worksheet. What you've done so far is you've learned how to just do the electron dot diagram. So in that lesson on Monday, you learned to do electron dot diagram. I'm going to simplify the math behind it and show you just, if you're looking at the molecule, can you start figuring out without doing the math of how many bonds go around each of the atoms. So if you notice right here, I have 1 carbon atom and I have 4 fluorine atoms. When you're looking at a molecule, and these are 2 nonmetals, so I know that the vocab word molecule is happening. The one in the least or less amount, which is carbon, because I've got 1 of them, compared to 4 fluorine, carbon then gets into the central atom. It's the central atom. And surrounding it, I have my 4 fluorine atoms. I'm going to move this away a little bit just so it's not in the way later when I'm going through information. All right, so I have my fluorine atoms. Now you had to figure out how many valence electrons, and this is from Unit 2 as well. We found a trend on the periodic table that each group on the top, it got rid of an electron, so it has 1 valence electron. The second one has 2, then it goes 3, 4, 5, 6, 7, all the way to the noble gases, which have 8. The only exception of the noble gas would be neon, which only needed 2. The main goal of all these electrons, again, we learned this in Unit 2 when we did electron configuration, its main goal is it wants to be more like a noble gas. So it wants somehow to have those 8 electrons, even though it can't just get electrons from anywhere. It's not that easy. So then we can figure out what happens in a molecule and how it becomes content, or happy, as I like to say it. So carbon, if you look on the periodic table, is in the 4th group over. We don't consider the transitional metals. So if you go 1, 2, 3, 4, let me see my finger right there, you'll see 4. So we know that carbon has 4 valence electrons. We'll draw those as dots surrounding carbon first. It clearly doesn't have 8. So it's not content. It wants to be like a noble gas, but it isn't. If you look and find fluorine on the periodic table, you'll notice it's a halogen. So it's all the way to the right on the periodic table, and it's got 7 valence electrons. So I will actually denote those as red just so we can notice. So I have 1, 2, 3, 4, 5, 6, 7. If you notice where my carbon and fluorine meet, we have a bond that occurs. This is one bond. It's called a single bond. You can have up to 3 bonds occurring, so you can have a single, double, or triple bond. In this case, we only have 1, so it's a single bond. We also learned from the video on Monday that to make it less messy or more understandable, we like to just connect these electrons just to show that they're paired up. However, there is no bond that occurs there. They're just paired up to make it less of just dots everywhere. So we're clearly denoting how many dots. So again, I'll go around, place the 7 electrons around each of the fluorine. And then I'll make sure I make it less messy. And then I'll make my bond between carbon and fluorine. And it looks like this. So that's what we learned Monday and Tuesday. And Tuesday I added a little bit extra and said, all right, so on A asked you, draw the Lewis dot. That's the Lewis dot structure. Part B said, okay, well now you need to identify, are there any unshared pairs of electrons around the central atom? Because this is going to help with the geometry. Central atom here is carbon. There are no unshared pairs. In fact, carbon is paired up with all 4 of its electrons are paired up with 1 of the electrons from fluorine, excuse me. So you have 0 unshared pairs. And there are actually 4 atoms attached to the central atom. Right? We have 1 fluorine, 2 fluorine, 3 fluorine, 4 fluorine. We have 4 fluorines attached to it. Well, let's make sure that my Lewis dot structure is actually correct. So this is a way to check to make sure that you haven't missed something. You need to see that the original carbon had originally the 4 electrons, but by sharing, remember you're going to hear that word a lot, by sharing an electron and making a single bond connected to each of the fluorine, it now has 8 total, and 8 electrons is what it wants. It wants to be like a noble gas configuration. Well, let's look at fluorine. It originally had 7, but by sharing 1 electron with a carbon, sharing it here, we're sharing it here, and we're sharing it here. And again, these drawings that I'm putting right now around each one of them is not necessary. This is my teaching to you to show you where they came from. So these now have 8 electrons by sharing 1 electron from carbon. And because of it, it now is happy as well. So this is a proper Lewis dot structure. So let's now look at letter C. So letter C is going to ask you to construct the 3-dimensional shape. And I'm going to wait till Monday to do that. So you're going to skip letter C, and you're going to go to letter D, E, and F. So let's look at D. And as I do number D, I want to toggle over to a PDF. And let me actually share the correct PDF that I want you to toggle over. The molecular geometry chart. So we have concluded that there are no lone electrons around the central atom, and there are 4 atoms around the central atom. So if you're looking at this chart, you'll notice that there's no lone pairs, 0. There's no lone pairs here. There's no lone pairs here. So we have a couple possibilities, but then we need to look and see how many atoms are around the central atom. In this case, the first one that's considered linear, it only has 2 atoms. Well, this one didn't have 2. It had 4 fluorines around carbon. All right, let's go to the next situation. Again, no lone pairs from the central atom, but there's 3 atoms. Nope, we had 4 fluorine, so it cannot be trigonal planar. Tri means 3, so that prefix comes into play from math class. You're going to remember that. Tri means 3. It doesn't have 3. Let's go to this one. Well, this has 1 lone pair. Can't be that because we have no. Well, this one has no lone pairs, no extra pairs of electrons around the central atom. And look, it has 4 atoms around the central atom. And that's exactly what we had. We had 1 carbon with no extra electrons around the central, but we had 4 atoms surrounding it. So the type of molecule it is considered tetrahedral. The prefix tetra means 4. Let's walk it over to the right with the examples. We have an example of what it looked like, and this exactly looks like what we had, except instead of hydrogens, we had fluorine molecule, or atoms rather. Now this is the actual molecular shape it has. If you notice, there's no 90 degrees. Electrons repel. So we've got electrons in all these atoms over here, and they repel each other. So they don't actually form what your Lewis dot structure shows you. They actually start to form 3-dimensional shapes. In this case, that little arrow that you see coming outward, that's coming out of the plane of the paper. Those dash marks that you see right there with my hand, coming back into the plane of the paper. And then you'll notice this is about at 109.5 degree angle, and it's showing you that right there. So these angles are approximately all 109.5 apart. So for that reason, I'm going to toggle back over to my Word document here. For that reason, the shape of this is considered tetrahedral. Okay, so you're skipping C until Monday's lecture, and then we're doing D. We're going to go to E and F because E and F are hand in hand. E and F is asking you information about each of the bonds, and in this case, we only have a CF bond. And F is asking us information about the entire molecule. And this brings me to a quick story for you. All right, so growing up, I have 2 older brothers and a younger sister. And when we went and got a treat, my mom and dad did not buy us each a chocolate bar. We usually had to share them. So maybe they'll buy 2 of us and they'll let the brothers share one and then the sisters share one. So me and my sister got a Hershey's chocolate bar. And I got one, and my mom and dad are like, here, share it with your sister. Okay, so what does a good sister do? They'll break the chocolate bar, and I give her one. I'm sharing it, right? But I'm giving her the side a little bit less. You know, I'm being sneaky. I'm giving her the side with a little bit less chocolate. But I'm sharing it. So when my mom comes back and says, oh, did you share it? Your sister's complaining. No, I shared it. We both got some. Clearly, I got a little bit more because I broke it, and I gave her the shorter end. So then my mom smartened up, and she gave me another chocolate bar, you know, whatever. She gave me another chocolate bar. And she said, okay, you're going to share with your sister. But this time, your sister gets to choose the side that she wants. So I'm frustrated because I'm like, well, I have to share it. But now, instead of breaking it up in unequally, I break it up as equal as possible. Like I take a ruler out, I measure it. You know, when you're kids, you want to get as equal as possible. So when I break it up, my sister, well, they're both identical pieces now, and she's sharing it with me, but now she's sharing exactly half of it, while before it was being shared unequally. So just like my analogy, atoms do the same thing. They are sharing electrons. Remember that word sharing. You're going to get sick of me, you know, saying that over and over again, but I want you to focus on the fact that they're sharing these electrons. They're sharing them to become more like a noble gas, that around each of these atoms, they have 8 electrons. But sometimes they share more, and sometimes they share less, just like in my analogy. So how do we figure that out? Well, if we're trying to figure out the sharing of a bond, we can look at something called electronegativity. And if you use my periodic table, you'll have the electronegativities. They're right located underneath of them. If you don't have my periodic table, you can toggle over to that worksheet that I have, electronegativity chart. And on that chart, I also typed up information about how to determine if something's being shared equally or unequally. There's vocab words attached to being sharing equally and unequally. So let's look. If we looked at that chart, whether it be the periodic table or the chart that I had you toggle over, we'll find that carbon has a value of 2.5 and fluorine has a value of 4.0. You always take the absolute value, that means there's no negative, and you take the difference. When you take the difference, it becomes 1.5. And that number to us doesn't make any sense until we look at that chart that I gave you that you can toggle over right now or look at later. When you look at that chart, you'll find that 0 to 0.4 is considered something non-polar. And now this is vocab words. And 0.4, so 0.41 to 2 is considered polar. Polar and non-polar are two vocab words that we're adding today. So polar means it's unequal sharing, and non-polar means it's equal sharing. So if we fall at 1.5, we become a polar covalent bond because I'm just looking at the bond. So between these two bonds, polar, so it's 4.0 and 2.5, each of these bonds were unequal pooling. They're still sharing, so it's unequal sharing, excuse me. So polar covalent bond. If it was falling 0.4 or below, it was considered a non-polar bond, and that would be an equal sharing. So again, we only have carbon fluoride. If you have other bonds within this molecule, you would have to individually tell me each of the polarity or non-polar of each of the bonds. Now let's look at the molecule. So that was just the bond. Another analogy of that, I'm going to just quickly, we have a couple minutes here. I want to use the rubber band to give you an example. So I have two rubber bands. It's like comparing me, Mrs. Sulkson to Joe Sulkson. Joe Sulkson is clearly larger and stronger than I am. As much as I want to admit that I'm stronger, he definitely is. So if I had my colleague and me, like we represent the rubber bands, and this paper clip is what we're pulling in between each other. If it's just me and my colleague, or me and my college daughter that are pretty similar, we're pulling on that pretty equally. So we'd be considered a non-polar, right? This is a non-polar bond. But the minute Joe Sulkson comes into play, he is clearly stronger than I, and I have to admit to that. So what happens is that he now is represented by a longer and bigger rubber band versus my smaller rubber band. You can't really see it that well in the picture here, but this right side is longer. So when you're pulling it, you can see that now my paper clip is being pulled more to the right because, again, I'm still sharing that paper clip, but it's unequal. So it's considered a polar covalent. Again, the word covalent is sharing. So let's see what happens with the molecule. This is just an individual bond. This is going to bring us back to physics class when we talked about vector diagrams. We are going to look at the molecule. I've addressed 4.0, the electronegativities, even though those are unnecessary. There's no subtraction here. You're looking at the pull. If you have a 4.0, like the Joe Sulkson, it's going to pull more on this side. So we're going to draw a line representing where it starts the pull, and the arrow is going to go towards the larger number. Let's look at this carbon to fluoride. Well, it happens to be carbon to fluoride all the way around, but I want to emphasize because it's not always going to just be carbon fluoride. This one's going to pull to this end. And then this arrow is going to be pulling here. So if you're noticing, they're all being pulled equally. And what we just learned from this lesson is that word equal pulling is considered non-polar. So my molecule, the entire molecule as a whole, is being pulled equally. So as a molecule, it's considered a non-polar, sorry about that, molecule, versus the bonds individually were unequal pulling, and we found that out by the difference of electronegativity. So when you're trying to find the bond, you're using the numbers and subtracting, taking a look at your chart. Is it falling between 0 and 0.4, or is it 0.41 and 2? So it's either going to be nonpolar or polar. If you're looking at what happens after 2, you're curious. After 2, you become an ionic compound. You no longer are sharing electrons. Ionic means ionizing, so you become charged. So we're not focusing this lesson on ionic compounds, but I'm not ignoring them either. Okay, so that's something to consider. So bonds are found by the difference of electronegativities. Your molecule is, you're going to draw those arrows and show the pull. And if they're being pulled equally, in all this case, they're being pulled equally, that molecule, it's considered nonpolar in this case. Okay, so that is possible to have both. All right, I am going to stop my sharing and stop recording at this point.